Kia ora everyone. Welcome to Lecture 1 for Week 1 in 162.04. Now, each lesson or each lecture will be associated with a particular section in the textbook. So in this case it's ZIL 1.1, so ZIL is the author of the textbook. So as you're going through the videos and the accompanying study guide, you should have the textbook at your side and initially just working out which section you're on, and then also referring to it for more details as necessary. Now this week, in week 1, we're not actually going to be solving any differential equations. We'll just be getting a feeling for what they look like, how to read them, what they mean, what the different terms mean, and there's going to be a lot of terminology. So again, as you are going along, it's a good idea to make notes of the key terms and what they mean, especially when you're reading the textbook, because it's a little bit dense. You need to approach it slowly and learn how to read textbooks, but they are explained in full detail and very, very clearly. That those explanations have been worked on in great detail. But if you come to a word that you're not quite sure of the meaning of, you should definitely stop and double check that you know exactly what it means. So first off, what is a differential equation? So we meet equations all the time, of course. That's the workhorse of virtually all of mathematics. But here we want to contrast algebraic equations with differential equations. So an algebraic equation would be something like x squared plus x plus 1 equals 0. And the point is that the unknown here is x. We're solving for x, and it might be a real number. So we write x as an element of a real number. So we're looking for a number in this case, and that one is a quadratic equation, so it could be solved with several ways. Use the quadratic formula, factor it, complete the square. There's various techniques. There's all sorts of techniques for solving algebraic equations. You've probably also met systems of algebraic equations where you have several equations and several unknowns. But differential equations are different because they have an unknown function. We're not looking for an unknown number. We're looking for an unknown function. For example, might be called y of x. And then the differential equation will involve the derivative and x and y itself and the unknown function itself. So a simple example that we're going to use over and over would be dy dx equals 2y. So if you read that out in words, you would say we're looking for an unknown function y of x such that its derivative, dy dx, is equal to 2 times the function you started with. Now you could perhaps come up with a solution of that differential equation just by trial and error, trying various functions y, plugging them in and seeing if they satisfy the equation or if they don't. We're not going to worry about that today. Eventually we'll do some techniques that let you solve lots of differential equations, but not all of them. So not all differential equations can be solved analytically to get a formula for the solution. We'll come back to that differential equation later. So here we're looking for y of x. Now the variables in there, the x and the y, they play a different role. The x in this case is called the independent variable, and the y in this case depends on x, so it's called the dependent variable. So the functions are the dependent variable. Now, in that previous example, we were just looking for one function, but you might be looking for more than one function, so I'll say variables. And they depend on some other variables that are the independent variables. Some other variables, maybe one or more than one, so they're called the independent variables. So the variables in different types of equations might have different names depending on what they're representing. So every time you see a differential equation, you want to be asking yourself and make sure you understand which is the dependent variable and which is the independent variable. So in this example here, x was the independent and y was the dependent. And you basically just need to look at the derivative terms. I'm differentiating y with respect to x. That generally means that y is a function of x, so y is the dependent variable. Now the next terminology is the difference between ordinary and partial differential equations. Ordinary differential equations are the ones where you've got one independent variable. For example, the one we just had, dy dx equals 2y. And partial differential equations, more than one independent variable. Now it's very easy to tell the difference because partial differential equations, the derivatives will have to be partial derivatives. You might remember this from 161.01 calculus. So for example, second partial derivative of u with respect to x plus second partial derivative of u with respect to y equals 0. That is a partial differential equation. Or that's often abbreviated PDE. So ordinary differential equations are abbreviated ODE. This particular one is a very famous partial differential equation. It's called Laplace's equation. It describes all sorts of things like steady-state distribution of heat or electrostatic charge. Comes up in fluid mechanics, comes up all over the place. But you can tell it's a partial differential equation because of the partial derivatives. And now I'm running out of space on my slide. Maybe I can write in here. I'm looking for a solution u of x and y. So x and y are the independent variables and u is the dependent variable. Now in this class 162.04 we're only going to be dealing with ordinary differential equations. So you'll hear the term ODE over and over again. We're going to be studying ODEs, but it's as well as the difference for things that come up later on. Now before I wrote the derivative of y with respect to x like that, but you know, if y is a function of x, you can also write dy dx equals f prime of x. So the prime notation is another way of writing the derivatives. And there's a third way that you sometimes see, which is a little bit slack, but it's often used. You just write y prime for the derivative of y with respect to the variable it depends on. And that's the reason for the different notations is that this notation here, which was invented by Leibniz, tells you what the name is of the variable you're differentiating with respect to. So that's very handy when there's more than one variable floating around. The prime notation here, which was invented by Newton, doesn't tell you exactly what they're differentiating with respect to. You have to tell from the context. And for second derivatives, you could write f double prime of x, you might write y double prime, you might write d squared y dx squared. And also for partial derivatives, there are more than one notation as well, just to make things more confusing. So where I wrote second partial derivative of u with respect to x, that is also sometimes written uxx with a little subscript notation. But we're not going to worry about that because we're not going to study PDEs in this course. Okay, so the first two things you want to know about a differential equation are what are the dependent and independent variables? Look for the derivatives. Is it an ordinary or a partial differential equation? And the next thing you want to know is the order. The order of a differential equation is the highest derivative. So for example, the one we had before, dy dx equals 2y. It's only got first derivatives in it, so it's a first order equation. If I have d squared y dx squared plus y times dy dx plus x cubed equals 0, getting a little bit more complicated. You just look along, look at all the terms that have derivatives in them. Whoops, d squared y dx squared. That is a second order. And again, as you've probably guessed already, first order equations are much easier to solve than second order. Second order is easier to solve than third order, but the key thing is once you've got to second order, you've basically already captured all the complexity that can come up in higher order. So you're more or less into the general case already. When you meet a differential equation, ask yourself, what is the order of that differential equation? Next, differential equations can be linear or nonlinear. Now, this takes a bit of thought. A linear differential equation is one, getting a little bit circular or tautological here, but the point is it has to be linear in y, which is the dependent variable, and its derivatives. So only terms like some function of x times some derivative of y, say the nth derivative of y with respect to x, are allowed, or just a function of x alone. So the x part can be a nonlinear function of x. A linear differential equation is defined by how it depends on y. So the most general nth order linear ODE, well, if it's nth order, that means its highest derivative term is dny dxn. And that could have a coefficient function, which could be any old function of x whatsoever. And then I could have an minus 1 of x, dn minus 1y, dxn minus 1. I keep doing the same mistake. All the way down to a 1 of x dy dx, the first derivative term. Then something with no derivatives, a 0 of x times y, that's a bit like the 0th derivative. And then you're also allowed to have a term which we traditionally write on the other side, function of x only. So these an up to a0 and g, they're called the coefficients. So if the equation looks like this, it's a linear ODE, otherwise it's not. So for example, do I have room to write in my equation? No, I have to write a little bit smaller. X cubed d cubed y dx cubed plus x dy dx minus 5y equals e to the x. That is a linear third order differential equation. Here's the third order term because it's got d cubed y dx cubed. There's no second derivative term, that's fine, that just means its coefficient is 0. And these coefficient functions, they're the coefficients, they themselves can be nonlinear. It's still a linear differential equation, so that one is a third order, and linear. But if I have something like this, d squared y dx squared plus sine y equals 0, that is second order and nonlinear. The second derivative term is all right, that first term is linear, but this sine y, that's a nonlinear function of y, that makes the whole differential equation nonlinear. Another example, 1 minus y dy dx plus 2y equals e to the x. Looks a little bit similar to the last one. It's a first order equation. It's just got first derivatives. But you see this problem term here. a function, the unknown function y times its derivative, that's the nonlinear term. And again, not too hard to guess that nonlinear equations are going to be harder to solve and also have a much more complicated behavior in their solutions and much more complicated phenomena that they can do than linear equations. But fortunately, lots of things in nature are described by linear equations, so they're important too. Okay, so to wrap up, let's just do some examples. Now here's where you get to do some work. So here are 6 examples, and for each one you need to pause the video so you don't see the answer too soon and say, what are the dependent and independent variables? Is this an ODE or a PDE, ordinary or a partial differential equation? What's its order? And is it linear or nonlinear? So I'll pause for a second to allow you to pause the video and jot down the answers for these 6 questions. Okay, so let's see how you went. So this first one, we've got d squared y dx squared. We've got x's and y's as the variable. So y is a function of x. So I'm looking for a function y of x. So y is the dependent variable and x is the independent variable. The order is 2 because I have second derivative of y. It's an ODE because I have ordinary derivatives, just one independent variable. And it is linear. If you look along, each term is a function of x times the derivative of y, or a function of x. The next one. Now here you see y and some derivatives. You don't see any other variable. So we have to assume, we just have to basically make up a name for the independent variable. And then y prime would be the derivative of y with respect to that. So let's call the independent variable x so that y prime is dy dx. Then y would be the dependent variable. Now I see that the order is 4 because I've got the fourth derivative of y. It's an ODE. Run along all the terms. Each term is a function of x. Well, you don't see any x's. That means that those coefficient functions are just 1 times the derivative of y, so it's linear. It's a linear fourth order ODE. That one would be easy to solve. Number 3, again, we're looking for y of x. That's easy. Order 2. It's an ODE. This time it's nonlinear. If you look at this term here, you've got some functions of x and y times a derivative of y. So that makes it nonlinear. Here I see the variables have changed names. I see d squared x dt squared. So now x is the dependent variable and t is the independent variable. Here I see d squared x dt squared. That's a linear term. And here I see a function of t, which is the independent variable, times x. So again, that means it's linear. It's second order linear. Here the dead giveaway is the curly d there for partial derivatives. So this is a PDE. X and y are the independent variables. U is the dependent variable. It's first order because I just see first derivatives. Now we didn't talk about how a PDE could be linear or nonlinear, but you can see that each term is just a function of x and y times the derivative of u. So this one is in fact linear. This one, we see some functions of x and we see some y's and derivatives, but we don't know what those actual functions of x are. So how we interpret this is that p of x and g of x, they're considered just to be arbitrary functions of x. We don't know what they are. They could be any function whatsoever. So this would be again, I'm looking for y of x. This would be a first order linear ODE. And in fact, because I've let the coefficient functions be any function of x whatsoever, this would be the most general first order linear ODE. Okay, so once you've finished the video, what you should do is immediately go away and do some problems to fix those ideas in there. And there's some suggested problems in the on the stream site. Once you've done those problems, you can move on to the workshop problems for the week. Okay, see you in the next lecture.